So now we are going to understand the concepts of method of moments and maximum likelihood estimation using Python. So if you can recall, we found the point estimators for the population parameters in uniform distribution, normal distribution, gamma and Poisson distributions. And for method of moments, we estimated basically these parameters in these distributions. Now here in Python, what we will be doing is that for each of these distributions, we will draw a random sample and calculate the point estimators we found in the first lecture of this week. By doing so, we would see how close your point estimators are to the population parameter. So let us begin with the uniform distribution. So let us first of all import the necessary libraries. Import numpy as np, and from scipy.stats. So scipy.stats basically provides various statistical distributions and functions. So from that we are going to import this uniform distribution. Now we are going to set numpy random seed. So we will use np.random.seed. So here we assign 123. So it basically means that we are basically using numpy's random number generator. And when we set this seed, it ensures that the random numbers generated in your code will be the same every time you run it. Okay, so it will not change whenever you run that code. So for that it is important to give this number over here. Next, we will suppose here in this case we are going to draw a random sample from uniform 0 theta. Okay, so let us take this theta as 8, and this means that we are going to draw a random sample from uniform 0 8. Okay, now we are going to generate a random sample from this, and what will be the size of that? Let us specify this as 100, and now we will use this sample to basically store the random variables that would be generated using this. So location is 0 because we are generating the sample from uniform 0 8. So LOC would be 0, scale in this case would be 8, and the size would be the sample size that we have already defined. Okay, so here we are basically generating a random data from a uniform distribution, and we are storing it in this variable over here. Next, we are going to calculate the sample mean. So we will use numpy's mean function over here. So data sample. Okay, and why are we calculating this sample mean? The reason is that in method of moments, when we were estimating the parameter for uniform 0 theta, then we found that theta hat came out as twice of the sample mean. Okay, so here also we will calculate that estimated theta, suppose this, so it will be twice of the sample mean that you have obtained. Okay, and now it should, let us see what is the answer. Let us first print the true theta that we had. Okay, so it will also print the estimated one also. So let us write it. So estimated theta would be this one. So here we are using again your f string over here. So this means here also we would specify this formatting, that is up till 4 decimal places. So what you can see from here is that the true theta that we took over here is 8, and the estimated theta, that is twice of the sample mean, is 8.02. So you can see that it is very close to the population parameter. So it also shows you that if you want to estimate the population parameter using method of moments also, then whatever estimation that you are doing, it will be very close to the population parameter. So this was your uniform distribution. So let me just mention over here, this is for uniform 0, 8. Okay, next one that we will do is your normal distribution. Normal distribution, so we will first set the parameters and then I would write. So for this also we need to import libraries. So numpy we already have, I can rewrite it, import numpy as np, and from scipy.stats this time we will consider your normal distribution. From scipy.stats import normal. Okay, let us set what are the sorry, it will be norm, it will not be normal. Yeah, so let us set the true parameters. So in normal distribution we have two parameters, mu and sigma square. So let us consider true mu, suppose it is 5.0, and we can take your true sigma. So if true sigma suppose is 2, if it is 2 it means sigma square is 4. So we are basically drawing a random sample from normal 5 with normal distribution with mean 5 and variance 4. Okay, now if we have to generate a random sample from this, so sample size suppose is 100, and the data we are storing it in this data sample. So it is going to generate random data from normal distribution. So here location is your true mu, because mu is the location parameter in normal distribution, and scale would be basically your true sigma that we have defined over here, and size would be the sample size. Okay, now once you have calculated this, now we will so now once you have found out this sample, we are now going to calculate the sample moments. For sample moments, if you remember, for normal distribution, sample mean and your n-1 over n times of sample variance, these are basically your estimators for normal distribution. So for that we need to first calculate the sample mean. So we will use numpy's mean function. So here we will write data sample, and sample variance likewise we can write np.var. Again we will write this one, sorry, yeah, data sample, and here we will also specify this dduf as 1, which basically reflects that we are considering the sample variance and not the population variance, and be the length of this data set. So length of this. Okay, now we will use this method of moments. So estimated mu would be, mu hat came out as sample mean, that is x bar. So this would be sample mean only, and estimated sigma squared would be n-1 over n times n-1 divided by n, okay, multiplied by the sample variance that we have obtained, that is s square. Okay, so estimated mu hat is x bar, and sigma square hat is n minus 1 over n times sample variance. Now we will print these. So print f true mu would be your true mu that we already have over here. Okay, and what will be the true sigma? It would be this value. So we want sigma square, so you can write this, and here we can actually take the square at this step. So first it will be evaluated and finally it will be substituted and printed. Now if suppose you, in the same way, you want the estimated one, so estimated mu would be estimated mu that you have obtained here. Okay, and what will be the estimated sigma square? So let us print that also. Sigma square, so it will be estimated sigma squared that we have found over here. Okay, yes, so true mu was 5, and as we have taken over here, and sigma square was 4, and finally when you used the estimators that you obtained for normal distribution over here, so that is x bar and n minus 1 over n times sample variance, then what you obtained is that estimated mu is 5.07 something, and here it is 3.846. Okay, so again you can see that they are very close to their true parameters. Okay, now we are going to look into the gamma distribution, and there in gamma we have two parameters again, alpha and beta, and we obtained their estimates also. So estimators, so we obtained their estimators. So let us see if it reflects the same thing over here also. So gamma, alpha, beta would be there. So let us first start and then I will write. So for this again we have imported numpy np, and you need from scipy.stats, this time we need gamma. Okay, because we are going to deal with the gamma distribution. Again we can set np, the random seed, np.random.seed as 0. So this would specify, so this would ensure that the random numbers generated will be the same every time you run the code. Okay, now let us assume that the true alpha, that first parameter, is 3, that is your shape parameter. So alpha, so this is 3, and your shape parameter beta, suppose it is 2. This is your scale. So we will write alpha, beta. So we have shape parameter and the scale parameter. Next we are going to generate the random sample. So sample size, again let it be 100 only, and the data sample. Now for generating this sample we will use gamma dot rvs. It will generate random sample from this. So here A is your true alpha, okay, and your scale is your true beta that you have defined over here. and size would be the sample underscore size. Okay, so here you have generated random data from the gamma distribution with parameters 3 and 2, alpha and beta. Okay, and what is the sample size over here? It is 100. Now we are going to calculate the sample moments. So here we need sample underscore mean. So that is basically found using your numpy's mean function. So this here we will write data sample and sample variance would be np dot var, again data sample. Okay, so sample mean and sample variance has been calculated. Now if you recall, what was the estimators in case of gamma distribution? So alpha hat came out as n times x bar square divided by n minus 1 s square. That's the sample variance. And for beta hat it came out as n minus 1 times s square divided by n times the sample mean. So let us write that, and finally we will compare the estimated parameters with this original one, the true ones. So here estimated alpha would be is n times the sample mean square. So here let me, for the sample size we have used 100, let me use n for this so that it would be easier to write. Let n be the length of this data sample. Okay, now we can use n. So n times the sample mean squared, this is divided by n minus 1 times. So n minus 1 times, so this one would be here, one more bracket, n minus 1 times your sample variance in the denominator, right? And estimated beta, so this is again n minus 1 times of sample variance. So let me just copy it from here. So n minus 1 times sample variance, the same thing comes in the numerator here, and it will be divided by n times of sample mean. Unlike here we have, so here in this case we have the sample mean square here, it will be just this. Okay, and when you substitute this value, now if you want to print that, so we can just directly print them also. If you want to give this command for print, that also can be done. So you can see that the true alpha was 3, and here the estimated alpha is 3.043, which is very close to it again. And let us see what is estimated beta. So that is 2.01. So, and the original one was 2. Okay, so this is how you can visualize your point estimators. Okay, so we considered uniform, normal distribution and your gamma distribution, and the next distribution that we considered was your Poisson distribution, which is from the discrete family. So let me write Poisson distribution with parameter lambda. So here we can take, suppose lambda as 3. So here we already imported these. So let me just, so once you have imported the library, it is not necessary for you to write it again and again, but sometimes you need to rerun the kernel, so that is why I am writing. So here we would write import Poisson. Okay, let np, this random seed we can set np dot random dot seed. So here we will set as 0, and let lambda, that is true lambda, be 3, as I mentioned over here above also. Now we are going to generate a sample of size 100 and data sample would be Poisson dot bs. So here mu would be your true lambda only, true lambda, because it has only single parameter. So size would be the sample size. Now lambda hat is what it came out as, the sample mean, x bar. Okay, so let us calculate the sample mean. Sample underscore mean would be obtained using this, data sample. Okay, and your estimated theta, or we can say estimated lambda, would be basically the sample mean that you have obtained over here. So if you want to print this, we can print it also. So f string, so let us first write the true lambda. True lambda was this value that we have defined over here. So we will write it in this way, and we will also write for the same thing for your estimated lambda. So here it would be estimated lambda. So this one would be here, this value we want to say. Okay, so true lambda was 3 and estimated lambda came out as 2.99 when we draw a sample of size 100. Suppose I make it 200. Let us see if there is any difference. So it is 2.945. Okay, it has improved, 2.945. And if I take it as 400, 2.945 is what? So you can see that it is 3.01. So as you are changing the sample size, it is getting updated and it becomes very close to the original one. Okay, so in method of moments we considered these 4 distributions only, and here also we have seen how your method of moment estimators that we were obtaining there, how close actually they are to the true parameter, right? And this must have given you some idea and some sense about how estimation works, right? Why do we say that, okay, if you are interested in the population parameter, rather you draw a random sample and study that sample, find the point estimator, and then point estimator would be very close to your population parameter. So here in each of these cases we found that it is actually very near to the true parameter, okay, or the population parameter.